Okay, so let's try some of these reactions out now. In section 12.3, we'll start to look at reduction of alkenes. And the way that we reduce alkenes is with H2 and a 10% palladium on carbon catalyst. Usually it's just written PDC like this, palladium / carbon. What that's for is that palladium is a very expensive metal, and if it's a catalyst, we don't need very much of it because it's not going to be used up in the reaction. It can keep being used over and over as the reaction progresses. So it's hard to weigh out a very small amount of palladium, but if you have palladium absorbed onto finely divided carbon, then that gives you a way to weigh out a really small amount, or to add a really small amount to your reaction. And what this does is it adds hydrogen on each side of the alkene. But if we take a more complex molecule, we'll find out something really interesting that happens that will help lead us to our mechanism. So now, if I take this alkene and add H2 with palladium on carbon, what I get is both carbons are on the same side, which means that both hydrogens added from the same side. So we get syn addition, and it's 100%. We don't see any anti-addition at all. So the question we should ask ourselves is why? Well, there's probably better drawings of this in your book, but I'll try and kind of draw it for you. What happens is that this is the metal surface, and the hydrogens get attracted to the metal surface. So here's 2 hydrogen atoms absorbed onto our metal surface. Then our alkene comes by, and this pi bond of the alkene complexes to the metal surface. And while that happens, while it's sitting there complex to the metal surface, it can start to react with the hydrogens. And so now the hydrogens start to be bonded to where the alkene was, and as the alkene starts to form the bonds with the hydrogens, it starts to let go of its complexation to the metal until the last step, when it's no longer attached to the metal at all and has full bonds to the hydrogens. So because of this, this alkene has to come and approach the metal from one direction or another, and the hydrogens that are all sitting on the surface will have to add to whichever side of that approaches. So it can come in sort of from the top or from the bottom, but whichever way it comes in, both hydrogens always have to be added to the same side. And if you want to see a better picture of it, you can look at mechanism 12.1. That shows a nice graphic of how this works. Now, what about reactivity of different alkenes as it relates to being hydrogenated like this? Well, if you think about it, if I have an alkene with only hydrogens on it, versus, at the other extreme, an alkene with 4 different alkyl groups on it. To make this reaction happen, this alkene has to approach the surface of the metal. This one would have the least sterics, or things that would be interfering with it approaching the metal. This would have the most steric interactions, or most steric difficulties approaching the metal. Which of those two do you think would be faster in being reduced with H2 and palladium on carbon? The ones with the least sterics are going to be the fastest. The ones with the most sterics are going to be the slowest. So this one's unsubstituted, this one's tetrasubstituted. So unsubstituted is better than mono, is better than di, is better than tri, is better than tetra, as far as the rate of reaction with H2 and palladium on carbon. So we can use this hydrogenation to help us better understand alkene stability. Back in chapter 8, when we started learning about alkenes, we said that a Z alkene is higher energy or less stable then an E-alkene. And we said that that's because of sterics. But like anything, if you want to really know what's happening, you have to go into the lab and calculate it and figure it out. So let's look at a reaction coordinate diagram. And I'll draw two reactions. First, I'll start with the Z-alkene being reduced by H2 and palladium on carbon to give butane. So this is Z2-butene, and it gives butane. And then I'll do a red reaction of the E2-butene with H2 and palladium on carbon, and that reduces to the exact same molecule, butane. Well, when we do these reactions, if we run these reactions, we can measure what delta H is. So delta H for the first one is minus 28.6 kilocalories per mole. It's negative because this product is more stable. We lost one pi bond and we gained 2 sigma bonds to hydrogen. We can do the same for this one. In this reaction, delta H0 equals minus 27.6 kcals per mole. So let's go back up to our reaction coordinate diagram. So it's negative, so that means our products are going to be more stable than our reactants. And so if I draw a reaction coordinate diagram for this, first one, and I can say, okay, so this is minus 28.6 kcals per mole. That's my delta H. So how would you draw the red one? Well, they make the exact same product, so it's ending at the exact same place, but now we only gain 27.6 instead of 28.6 kilocalories per mole. So as I go up here, now my delta H0 here is only minus 27.6 kcals per mole. So what that actually showed us is right here, there's a difference of 1 kilocalorie per mole in the stability of the starting materials, or in the stability of these two alkenes. So if you remember when we talked about degrees of unsaturation before, we said that every degree of unsaturation comes from either a pi bond or a ring. And previously we said that there wasn't a way to tell a difference between the two, at least not that we had talked about yet. So we can use hydrogenation to give a difference. So if I have a molecule C10H16, it's unsaturated because the fully saturated one would be CnH2n plus 2. C10H 2 times 10 plus 2, so H22. So if I have C10H22 minus C10H16, I'm missing 6 hydrogens. It takes 2 hydrogens for each degree of unsaturation. That gives me 3 degrees of unsaturation. Now, at this point, I don't know whether they're rings or pi bonds. So what I can do is if I take that molecule, C10H16, perform catalytic hydrogenation on it, the reaction that we've just been learning, and I get C10H20. Now I actually know exactly how many rings and exactly how many pi bonds I had in the molecule, because here I added 4 hydrogens by catalytic hydrogenation, which means that I had 2 pi bonds that have just both been hydrogenated. And if there are 3 degrees of unsaturation and 2 of them are pi bonds, then it also has 1 ring in the original structure. So it's one of the ways that chemists could actually learn structures of different molecules, how many rings, how many pi bonds they have